This video is about alkenes and their electrophilic addition reactions. Alkenes are unsaturated hydrocarbons. They have the general formula CnH2n. The simplest alkene is ethene, the one with two carbon atoms and a double bond. The functional group of alkene is the double bond between the two carbons. The double bond is formed of one sigma bond and one pi bond. There is no rotation around the double bond for alkenes. This is why alkenes can have different isomers, which are called the Z and E isomers. If you want to learn more about the isomers of alkene, please have a look at the video link in the description below. To name alkenes, first of all, you need to identify the longest chain carbon. Here, the longest chain has 6 carbon atoms. Then you need to start numbering the chain, and you start numbering in the position which gives the double bond the lowest possible number. In this case, we started the numbering from the left because the double bond here on carbon number 2. The root name here is going to be 2-hexene. And then we look at the substituents. We have a methyl group in carbon number 2. So the final name is 2-methyl-2-hexene. Dienes are hydrocarbons which have two double bonds in the same structure. To name dienes, we need again to find the longest chain of carbon atoms that have the two double bonds and then start numbering, which gives the two double bonds the lowest possible number. And then as normal, we're going to name it using the suffix diene. So for example, when we have this chain or when you have this compound which have 5 carbon atoms, we have double bond here on carbon number 1 and the other double bond starts on carbon number 3. So the final name is 1,3-pentadiene. Electrophilic addition reactions of alkenes. Alkenes are electron rich because they have double bond. This is why alkenes can undergo several reactions compared to the alkane. The most the double bond of the alkene of alkenes is broken, and then two new bonds are formed with other atoms. The double bond is rich in electrons and it can be attacked by electrophiles. So what is an electrophile? For any new bond to be formed, usually we have a nucleophile and we have an electrophile. A nucleophile is a species that is electron rich and it donates its electron and moves its electron towards an electrophile, which is an electron deficient, and then a new bond is formed due to the movement of the electron from the nucleophile to the electrophile. So let's have a look at what are the nucleophiles, what type of nucleophiles are there. First of all, nucleophiles can be species that have lone pair. For example, ammonia, which has a lone pair, or an amine, water, or an alcohol. All of these have lone pair of electrons and they can act as nucleophiles. Also, a nucleophile a species can have a negative charge, something like hydroxide ion or a bromide. All of these have a negative charge and they can act as a nucleophile where they can donate their electrons to an electrophile. An electrophile as well can be carbon-carbon double bond, which is electron rich, like the alkenes. So alkenes themselves are nucleophiles and they react with electrophiles. They donate their electrons to electrophiles which are electron deficient. So in all of these cases, as we can see, the electrons moves from the nucleophile towards an electrophile. So examples of electrophiles. Electrophiles can be a positively charged ion, like hydrogen plus, or can be an atom that has a double bond to an electronegative element, for example, like the carbonyl group. So in carbonyl group, the double bond between the carbon and oxygen, the electrons can move towards the oxygen because of the oxygen is highly electronegative. And then this is an electrophile where a nucleophile here can donate its electron or attack the electrophile and donate its electron to form a new bond. The third type is a single bond, which is attached with if an atom has a single bond to an electronegative element. In this case, like hydrogen chloride, the chloride is more electronegative than the hydrogen, so the chloride will be partially negative and the hydrogen will be partially positive. In this case, the hydrogen is the electrophile and it can be attacked by a nucleophile. In a reaction, when we have nucleophile and electrophile, you're going to find the curly arrows, which indicates the movement of the electron from the nucleophile towards the electrophile where a new bond is formed. When a new bond is formed, normally another bond is broken, like here in the reaction between ammonia and hydrogen chloride to form ammonium. The new bond between the nitrogen and hydrogen is formed, while the chloride has left with a negative charge. The reactions of alkenes, the first reaction is the halogenation, which is addition of bromine. So the mechanism of this reaction goes as follows. First of all, the bromine is a nonpolar, but when the double bond of the alkene approaches the bromine, it starts to polarize this bond. So the first bromide will become partially positive while the other one becomes partially negative. In this case, we have the nucleophilic center, which is the double bond, and we have the electrophile, which is the bromide with the partially positive charge. The electrons on the double bond will attack the bromide with the positive, partially positive charge, and then the other bromide will leave with the electron. Now, the bromide will be added, the the electrophilic bromide will be added to the carbon, and the double bond will be broken, and that will leave a positive charge on the other carbon. This is called a carbocation. Now we have the other bromide with the negative charge. This is going to attack the carbocation, the carbon with the positive charge, and then that will lead to the final addition product where two bromide have been added to the double bond and the double bond has been completely broken. This is called electrophilic addition reaction, and the product is 1,2-dibromoalkane. The reaction between alkenes and bromine will give you 1,2-dibromoalkane. This reaction is used, bromine water is used to test for double bonds. This is because the bromine water is orange in color due to the presence of bromine. And if you have some solution or if you have a sample with um, an alkene and you add few drops of bromine water and shake, then the bromine will react with the double bond to give 1,2-dibromoalkene. There will be no more bromine available, so the color will change from orange into colorless, which indicate the presence of a double bond. Alkanes, which don't have double bonds, do not undergo the same type of reaction. So if you only have alkanes and you do this test, there will be no change in the color of the solution and it will remain orange. Electrophilic addition also can be seen with polar reagents because we said bromine, the halogens are nonpolar. So also with the polar reagent, we can see this reaction. In this case, we have the double bond of the alkene and which is the double bond is the electron rich center. And then we have the polar reagent. In this polar reagent, we have one atom which is partially positive and the other one is the partially negative one. Of course, B here will be the more electronegative atom or group of atoms, and A is the less electronegative one. In this reaction, the general scheme, we're going to have the double bond is going to attack the uh, partially positive atom, while the other one is going to leave as a negatively charged one. The A will be added first to one of the carbons, and then the B will attack the other carbon, and that will lead to formation of the addition product, where A is added to one carbon and the B is added to the other one. So an example of these polar reagent is the hydrogen chloride. So let's have a look at the addition of hydrogen chloride. So in this reaction, we have the hydrogen chloride where the hydrogen is partially positive and the chloride is the partially negative part of the compound. And then we have the double bond, which is the electron-rich center. This is going to attack the partially positive hydrogen, and then the chloride is going to leave with the electrons. In this case, the hydrogen will be added to the first carbon, and that will leave a positive charge on the second carbon. And then the chloride is going again to attack the carbon with the positive charge, and the chloride will be added in the second step, and that will give us the product, which is the halogen alkane. So the example we've seen was addition of a hydrogen alkane to a double bond of a symmetric alkene. A symmetric addition of hydrogen chloride to symmetric alkane. Symmetric alkanes means that the two carbons of the double bond have the same number or the same substituents basically, so they are exactly the same. So the product, wherever you add the hydrogen to the first or the second carbon, you're going to end up with the same product. But sometimes you need to add hydrogen halide to an asymmetric alkene. Asymmetric alkene is one like this one, where we have the two carbons in the double bonds. They have different substituents. So the first carbon has two hydrogens, the second one has a methyl group and has a hydrogen. Then you have the hydrogen bromide that will undergo the electrophilic addition reaction. The double bond will attack the hydrogen, which is the partially positive end of the product, and then the bromide will leave with the negative charge. So in this case, you have two possibilities because the hydrogen can be added either to carbon number 1 or carbon number 2. So if the hydrogen adds to carbon number 2, that will give us an intermediate, which is a carbocation with a positive charge on carbon number 1. The second one is if the hydrogen adds to the carbon number 1, then this will give us a carbocation with a positive charge on carbon number 2. These two are different and they will give us different product because the second step for the first one, if you have the bromide, it's going to attack the carbon number 1, and the final product is going to be the 1-bromo propane. In the second case, you have the bromide is going to attack the carbon number 2, and then you're going to end up with 2-bromo propane. So there are two different products now. So are these two equivalent, or are these one of them will be a major product and one is going to be a minor product? Actually, they are not equivalent. The whole idea is about the stability of the carbocation that has been formed in the first step. So these two carbocations are not the same. So let's have a look at the reaction intermediates, the carbocations and their stability. A carbocation is an ion with a positively charged carbon atom, like the one we just have seen. The stability of carbocations, we have four different types of carbocations. We have the methyl carbocation. This is the methyl one, which has a carbon with a positive charge attached to three hydrogens. And then we have the primary carbocation. This is the one where it's only attached to one carbon and two hydrogens. And then we have the secondary carbocation. This is the one that has two carbons attached to it, and the tertiary one has three carbons attached to it. In case of stability, in order of stability, the tertiary will be the most stable, followed by the secondary, followed by the primary, and then the methyl is the least stable. The reason behind the stability of these carbocation is because the carbon atoms are electropositive atoms and they tend to push the electrons towards the positively charged carbon. That leads to an increase in the stability of the carbocations which has the positive charge. In case of tertiary carbocations, we have three different carbons all pushing their electrons toward the carbon with the positive charge. In case of secondary carbocations, we have two carbons which push their electrons, and in the primary we only have one carbon atoms pushing its electrons toward the positively positively charged carbon. So the more the number of carbon atoms that push their electrons toward the positive center, the more stable the carbocation. The more stable carbocation means that it will be formed as a reaction intermediate. So let's go back to our reaction. So the reaction between one propene with hydrogen bromide. So the first step will lead to formation of two different carbocations. The first one, if the hydrogen adds to the carbon number 2, in this case that will give us a primary carbocation because this carbon with a positive charge is only attached to one carbon atom. The primary carbocation is the less stable one. The second case here, when the hydrogen adds to the carbon number 1, in this case, as we've seen here, the positive charge will be on carbon number 2. This is a secondary carbocation because the carbon here is attached to two different carbon atoms. This is one and this is the second carbon. So this is a secondary carbocation which is more stable, meaning that this will be formed more than this one. So the second step of the reaction, the bromide is going to attack the carbocation and that will give us the 1-bromopropane. This is going to be the minor product because the carbocation or the reaction intermediate will be formed less than the other one, which is the more stable. So the second case here, the secondary carbocation that has been formed, the bromide will attack the carbon number 2 and that will lead to formation of 2-bromopropane, which is the major product due to the higher stability of the secondary carbocation compared to the primary one. Finally, there is the addition reaction of alkenes to sulfuric acid. So sulfuric acid can be added to alkenes in an electrophilic addition reaction in the same way as we seen for hydrogen bromide and hydrogen chloride. In this case, we're going to have the alkene and we're going to have the OH of the sulfuric acid. So the OH of the sulfuric acid, the oxygen is more electronegative than the hydrogen. So this is going to have an partially negative and the hydrogen will be partially positive. The first step in the reaction, the double bond of the alkene will attack the hydrogen and that will lead to addition of the hydrogen to the carbon and the formation of the carbocation where the double bond will break. At the same time, the bond between the hydrogen and oxygen will break and that will lead to the formation of the anion here, which is the hydrogen sulfate anion. The second step is that this hydrogen sulfate, this oxygen with a negative charge, will attack the carbocation, the carbon with the positive charge, and that will give us the first addition product, which is the ethyl hydrogen sulfate. So this is the original addition product of the sulfuric acid with the ethene. So if you add warm water, in this case, this is going to break the bond between the carbon and oxygen is going to break, and this is going to give you ethanol and will give you back the sulfuric acid. So sulfuric acid here has been regenerated as it started, and the final product is ethanol or is the alcohol. So the role of the sulfuric acid here is going to be simply a catalyst. So the final reaction is we add ethene with water in presence of sulfuric acid, which is going to act as a catalyst to give you ethanol as your final product.